Why are phase change materials complex for cooling design? Have you ever wondered why some materials are so tricky to use in cooling systems? Phase change materials, or PCMs, are a perfect example. They can be great for thermal management, but they come with their own set of challenges. Let's break down why these materials can complicate cooling design. First off, PCMs usually have low thermal conductivity. This means they struggle to transfer heat efficiently. When a PCM is supposed to absorb or releases heat, it can take longer than desired. To tackle this, engineers often add features like fins or other conductive materials to help heat flow better within the PCM. Another challenge is the volume change that happens during phase transitions. When PCMs melt or solidify, they can expand or contract by 10 to 20%. This shift can put stress on the containers holding the PCM, which might lead to leaks or even failure. Designers must create containment systems that can handle this expansion without breaking. Choosing the right material is also not straightforward. PCMs come in various types, each with different melting points, heat absorption rates, and durability. For instance, paraffin wax is popular because it is chemically stable and cycles well, but it has low thermal conductivity and significant volume changes. On the other hand, hydrated salts can conduct heat better and change volume less, but they can be corrosive and less reliable over time. Designers have to weigh these trade-offs carefully based on what the cooling system needs. Durability is another key factor. PCMs need to melt and solidify repeatedly without losing their effectiveness. Some materials might degrade after many cycles or if they get too hot. This can impact the reliability and lifespan of the cooling system, so managing the temperature of the PCM is essential. Subcooling is another issue that can arise. This occurs when a PCM stays liquid even below its melting point, which can delay solidification and reduce cooling efficiency. Additionally, some PCMs do not melt or solidify uniformly, which can create multiple phases and make thermal management unpredictable. Safety and environmental concerns also play a role in the design process. Some organic PCMs, like paraffins, can be flammable, limiting where they can be used. Others might be corrosive, requiring special materials for containment. Designers must take these safety factors into account to ensure everything operates smoothly and meets regulations. From a practical standpoint, integrating PCMs into cooling systems often means combining them with other technologies, like liquid cooling loops or heat exchangers. This adds another layer of complexity in terms of system control and packaging to ensure everything works well together. In summary, the challenges of low thermal conductivity, volume changes, material selection, durability, subcooling, and safety considerations make phase change materials complex for cooling design. Engineers must carefully navigate these factors to create effective and reliable cooling systems that utilize the unique properties of PCMs.